Good day. You are looking at your chemical bonding notes. This is our intro PowerPoint about chemical bonding. So chemical bonding is a description of what holds atoms together. Why do they stick together? Well, weird order. We know bonds form via chemical reactions. And we're going to worry about individual bonds in a molecule. Most of the bonding we're going to look at will be different types of covalent bonding, although you're responsible for ionic bonding. And ultimately what we're trying to do is get to the shapes of molecules and trying to get to shapes that represent what the actual molecules would be like. So we have four different materials. This is an element, then we have compound, compound, compound. This one is only going to have covalent bonds, and it's only one place for what's called a triple bond. This one is going to end up being a linear shape, might even have polar bonds, but it's going to be a non-polar molecule. This is going to be a polar molecule, and this is going to be ionic. Now, the usual thing, we start with mumbo jumbo, and by the end of the unit, this stuff should make sense. So because they have different types of bonds, different shapes, it's going to determine that they have very different properties. So chemical bonding, what we're doing is we're putting atoms close to each other, but they can't be too close and they can't be too far away. We need the right overlap of electrons. If they're too close, we get too much overlap of electrons, too much repulsion. That's not going to be stable. They're trying to minimize their potential energy. Things in the world tend towards lower energy, and this is an example of it. There is something called electronegativity. And what this does is it describes the attraction of an element for a shared pair of electrons in a covalent bond. And the scale essentially goes from 0 to 4. And so if you look at fluorine, it would have electronegativity of 4. So it really wants to pull in those electrons. On the other hand, something like cesium might have electronegativity of 0.7. And that means it really doesn't want to pull electrons towards it. So when we look at electronegativities, what we're going to do is we're going to compare the electronegativities of the elements in a bond, and we'll see which kind of tugging we're going to get. So there's fluorine, the number 1 at 4.0, and cesium's tied for last at 0.7. Turns out the difference in electronegativities is the key in this game. This is a chart that you should have. It's not one you memorize, it's one you can use. And here we have the 4.0, here we have the ones with the 0.7. And we have some 3.5, so oxygen tends to want electrons as well. And you'll notice that the noble gases don't have electronegativities because they typically don't form bonds. But this is a chart you'll use regularly to figure out the nature of a bond. So if we look at SO2, the sulfur is 2.5, the oxygen is 3.5, so the difference is 1.0. And by definition, that is called a polar covalent bond. So the oxygen ends up being slightly negative. It had the bigger number, it wants the electrons more than the sulfur. And the sulfur, because it lost, or those paired electrons moved away towards the oxygen, it becomes slightly positive. Now you might be saying, what's that goofy symbol? Well, you might have heard of a big D, and you might have heard of a little d. Well, these things are Greek letters. Big D corresponds to delta in the Greek alphabet, and little d corresponds to little delta. So that's just a little delta. And because it's partial, that's why they use the lowercase of delta. Little Greek lesson there. So at some point we're going to assign questions like this that show that you understand the meaning of electronegativity and how to use them in determining types of bonds.